Hello, everyone who's tuned in, either to the live presentation or to the recorded version of this. We're pleased to have in this week's seminar Dr. David Dill, and he has a distinguished career in academia and now in industry. He's well known for working in a number of areas, including some formal aspects of computing, and another area where I know him very well is the work that he's put into helping make sure that voting is conducted securely and safely. He's going to talk to us today about a formal verifier for blockchain language, and formal verification has some deep connections to potentially making systems more secure and more trustworthy. As we go along, if you have questions, please put them in the Q&A, and David will be checking that from time to time to answer the questions, and at the end of his talk as well. So without further ado, the esteemed Dr. David Dill.
Thank you. As an administrative thing, it's difficult for me to check the Q&A while using PowerPoint here. So if we could appoint someone, say SPAF, to interrupt me if there's a question pending, then I'll be able to address it. I'm especially interested in questions, as I was mentioning earlier. I have given versions of this talk mostly to audiences that are quite familiar with formal verification. I don't want it to go over people's heads. So I'm especially interested in hearing questions if you feel that I've left you behind, because it wouldn't take me too long to explain the basics of anything to get everybody able to understand the rest of the talk, or at least so I believe. Anyway, thank you for inviting me to speak today. I'm a blockchain researcher for Novi, which is a Facebook company that develops applications for the Diem blockchain. The research I'm presenting today is one of Novi's contributions to the blockchain. So you may have heard in the news the term the Libra blockchain over the last couple of years. The formerly Libra Association changed its name from Libra to Diem last December, and so that's why I'm talking about the Diem blockchain now. So the work I'll describe today is the results of the efforts of many people. So I hope that I provided some vision. I did some of the work, but it's mostly other people on the project. There's a prover team that's had some people moving in and out, but there's a core team of 4 or 5 people, some other people who've dropped in for a while and worked on some aspects of it, and several different interns that have done good work in the project over the last couple of years. There's also a team for doing the Move language. We call it the Move platform because it consists of the language design, the usual compiler stuff, a virtual machine, and code to interface the virtual machine to the rest of the blockchain. And so, of course, they've had their own interns. So it's more people that I can actually name in the talk here. Let's see here. Good. So first I wanted to say a few words about what Diem is. So it's a payment system. It's a blockchain, and hopefully at some point in the future we can expand it to be a broader range of financial services and maybe even other services. Novi is one of many organizations that will build applications for this blockchain, or so is our vision. And the first Novi application will be a digital wallet. So we'll have a payment system and you'll be able to use this wallet to store and transfer funds. Good. So the Diem Association exists so that Facebook doesn't control this. It's the Diem blockchain is sort of like the interstate highway system, and applications on it are like trucks that are trucking goods or have businesses that rely on that road system. So we have 27 Diem Association members, and they are global companies, venture funds, non-governmental organizations, etc. And so we've got diverse group of people, some of whom are very interested in providing financial services, others of which are representing a constituency of people who need financial services. In the talk, I'll be presenting some background on basic questions like what's a blockchain and what are smart contracts. I'll then talk about the move prover, which is the main topic of today. I'll talk about using the prover, particularly writing specifications. I'll talk about a particularly novel aspect of the prover, and I'll make some, which is the memory model, and I'll have some concluding remarks to summarize. So why are we doing this? A blockchain is a high assurance system for several reasons. There are large assets at stake, but it's a little worse than, say, a bank or the stock market where there are also assets at stake. Transactions on a blockchain are ideally irreversible. Now, in reality, they can be reversed, but it's difficult and there's some reputational cost. It's embarrassing if you find yourself having to reverse a transaction. So it's more important than many applications that we get things right and that we get the code right. The blockchain may be targeted by highly motivated, well-resourced adversaries. There was a story at one point that North Korea was funding weapons of mass destruction by cryptocurrency fraud. So we would prefer not to be involved in that, to say the least. And so already hundreds of millions of dollars in losses have occurred from bugs on other blockchains. There are more losses from bugs in wallets and whatever. I'm just talking about the core blockchain technology that stores the results of stores accounts and the results of transferring funds, etc. So we've got a bad track record and in the blockchain world, and so it's very clear that we need to do something about it. So the move prover is an effort to address these concerns. It's a formal verification tool for smart contracts on the Diem blockchain. So I'll concede that it's a work in progress. So it's improving over time. We've met some initial goals, but it's by no means complete. And so this is a status report on how it's going in some sense. And I'm going to treat it as an engineering project. It's not really a collection of research results. It's a real piece of software that's going to do real work. We hope we'll be writing more papers. We expect to be, but this presentation is really about a practical artifact. The system is 100% open source and is available on GitHub under Diem. And so here are our goals, some of which we've actually met. We want to allow complete specification of functional properties of smart contracts. And by functional properties, I'm excluding things like performance, timing things, or things that are probabilistic. So basically you have functions that change the state or have pre or post conditions. You have properties that are true over time, and they can be written as logical properties. The status of that is that we can't say that we have complete specifications, but we've actually got extensive specifications of the system that we're expecting to deploy. We'd like to enable fully automatic verification that the code implementing something meets its formal specifications. And we'd like it to run only a little slower than a compiler. This is in contrast to some efforts in formal verification, which involve basically proof checking. So it's an interactive system where a user enters a detailed proof of correctness of the system, and the proof system checks that the user hasn't made any errors in generating that proof. So this is another part of the design space for formal verifiers, which is automatic proof. The system right now can re-verify after every change in a smart contract interactively. So the idea is you're writing your smart contract, you change something, you can recheck the specifications automatically very quickly, and also in continuous integration. So I'm embarrassed to say that once I left the ivory tower and joined the real world, I learned that the way companies work is with large software systems, is that every time new code is checked into the system, a series of tests runs automatically. And normally people wouldn't think that formal verification would be fast enough or reliable enough that you could run it as part of that process, but we do it routinely. Every time we put in new code, the formal verifier runs on everything. So formal verification is hard. This is one of my research findings, having worked in the field something like 35 or 40 years now. And there have been many disappointments. And so I had to stop and think when I was starting this project of why don't I expect this to be a disappointment? And there are several reasons. One of them is we're starting with a clean slate. If you decide that you're going to build a formal verifier for Java, which would be a very useful thing, you're going to be have masses of existing Java code, a massive Java programming environment, a language that was not designed specifically for verification, etc. You're going to have a hard job. But we're starting with a blank slate where we can optimize to make formal verification doable. So we can avoid some of the problems, or we think we can avoid them, with verifying traditional software. So one thing is that developers don't expect to write specifications. They write millions of lines of codes with no formal specifications. We have a system that requires separate specifications in addition to the code. It's like assertions of various kinds. And we're just going to have the expectation that those will be written with a smart contract, and maybe it will be required at some point before somebody can put a smart contract on our blockchain. That decision has not been made yet. In general, programming languages are too complex and ill-defined to verify. You're writing logical specifications, you need to know precisely what every construct in the programming language does, and often that work has not been done. Another problem with programming languages, which I didn't put on this slide, is that they have large native libraries often, and those are especially hard to model. In our case, while we haven't been as careful about formal semantics of our language as perhaps we should have been, it is well defined and we understand it very well. Another problem in the traditional software world is that programs are too big and complex really to verify. One of the advantages of working in the smart contract area for blockchains is that smart contracts are generally simple compared with ordinary software. And finally, in the real world, and this was a sad discovery for me many years ago, people often don't care that much about bugs, even when they really should, because they're kind of in denial about the costs and risks incurred by those bugs. And so they don't put enough effort into avoiding them. In fact, some commercial tools for checking software, the most important thing is to figure out how to rank all the reports so that people can fix the worst bugs because they don't even care about fixing all of the bugs. So we care. I'm not sure what more to say about that. So we're in the happy situation where we can co-design our tools, including the formal verifier, also the programming style for writing smart contracts, and the verification methodology to try to optimize the conditions for success of formal verification. So I'm going to pause for a moment and see, does everybody feel like they know what I'm talking about with formal verification, et cetera? So we'll see some examples of specifications, and hopefully that will make it more concrete. If everybody's happy to just have me proceed now. So, there's a lot to know about blockchains, and here is the minimum that we need to know. A blockchain is a sequence of states. The states might be very large. It's essentially a complete database of accounts and maybe various other things that have been stored. It could be an archive for information. And transactions are program executions that update one blockchain state to create the next blockchain state. So in the diagram here, I've drawn a sequence of alternating states and transactions. The transactions are what change one state to the next. A smart contract, the idea started off as being a precise legal contract written in code, but nowadays it really just means a code that implements a transaction. So it's code that updates the blockchain. Transactions are atomic, so they either run to completion or they don't change the state at all. You don't get partial changes in the state in these systems, particularly not in ours. And I'm shading the truth a little bit here because a transaction, the user who submits a transaction has to pay for the computation. That's something usually called gas. And so a user will find that their account balance has been decreased a little bit, even if they have a failed transaction. We're not modeling that in this system. We've chosen not to do so. So let's look at the blockchain state in a little more detail. So in our system, the blockchain state is a tree and or maybe a forest, and the roots of the trees are numerical addresses. So these are large numbers. And at a particular address, you can publish an instance of a type. So these types are generally records, they're structs. And so in the example that I'm displaying here, address 2 has a published struct of type Diem account. So you can have 0 or 1 instances of every type published at a particular address. You can't have more than one instance of a type published there. So in our system, a Diem account has quite a few fields. There are 2 of them shown here. One is an authentication key, which is essentially a string, a vector of bytes. Another one is a sequence number. So sequences are submitted by, they're signed by accounts. The signatures correspond to individual addresses, and there's a sequence number for each address for the transactions that originate at that address, that are assigned by that address. And so the sequence number is maintained in the Diem account. We have other things that are published at addresses in our system. One of those things is a balance. Now, our language has type parameters. So in this case, balance is a generic struct, which is parameterized by a currency type. And one of the currency types in our system is XDX. A balance struct has a field also called balance, and that field contains a coin struct, which is also parameterized by the currency. The coin struct just has a value in it, which is the amount of currency represented by the coin, maybe the denomination if you want to think of it that way, and that's a 64-bit unsigned integer. You can have multiple currencies. So I said you can't publish the same type twice, but in this case it's a parameterized type with different type parameters. So we can also have a balance with the currency type XUS published. That, of course, has a balance field, which is also a coin, parameterized by XUS, which has its own value field. So I'd like to talk a bit about the Move programming language. This was invented at Novi. And so it's a programming language for implementing smart contracts on the Diem blockchain. I'll mention that the Diem blockchain, there could be other blockchains, or we're looking at broader applications of the Move programming language, but initially we're planning to target the Diem blockchain. So Move is designed for safety for applications like a blockchain. So, and this is also based on a sad experience of other blockchains using less safe languages. So in Move, the modules can only call modules that already exist. So the dependency graph of modules has to be acyclic. Other blockchain languages have reentrancy issues. So you can have a smart contract that calls a function in another smart contract. That other smart contract can recursively call back to the function that called it. And there have been millions and millions of dollars stolen and lost because of problems like this. So we just don't allow that. And we have a special type of structure called a resource type, which models physical assets. And so what that means is, in type theory, this is a linear type. It's a type that cannot be deleted or duplicated except by the module that defines the type. So for example, you can represent a coin. You could have a module that creates a coin, have a function in that module that creates a coin and returns it. And then other modules can only pass the coin around. They can't delete it or accidentally lose it or copy it. The Move language has limited expressive power. This may seem like a bad thing, but if you're trying to analyze or particularly formally verify a piece of software, your ability to do that is inversely proportional to the expressive power of the language. So what you'd like is a language just strong enough to say what you need to say, and that means you'll be able to maximize your ability to verify properties of programs in that language. Compilation of Move is a traditional looking process. You start with the Move source program, you put it through a compiler, and that generates, in our case, bytecode, which is not directly machine code. Like Java, we have a bytecode verifier that does semantic checks on the bytecode. The compiler also does the same semantic checks in order to be able to report errors intelligently to the user who needs to fix the program. But we're relying on the semantic checks that are done on the bytecode itself, because we don't want to have to trust the compiler. We'd like to remove the compiler from the trusted computing base and just rely on the properties of the bytecode itself, because it's the bytecodes that are deployed on the blockchain. So there's a separate bytecode verifier. I want to make clear that even though I'm using the V word for the bytecode verifier, it is not a formal verifier. We're just using the same terminology that's been handed down to us from other languages like Java. It's a semantic checker that runs in polynomial time. Good. So as a matter of architecture and and security and sanity, we have a policy that every change, or almost every change in the blockchain state, goes through the move virtual machine. So blockchain state at any point in time is a database that we're updating, reading and writing. And so what we want is that the thing that does the reading and writing to that database is the move virtual machine. The move virtual machine executes transaction scripts, which are written in the move language, actually the bytecode for the move language. And those scripts can call library functions, which are on modules also written in the move bytecode language, which are stored in the blockchain. All of the basic functionality of the blockchain is implemented in smart contracts. So that includes the currencies, concepts such as accounts and things, say, the access control rules associated with the accounts, and lots of other stuff. So let's talk about the move prover, the main topic of this talk. So it's a formal specification and verification system for move programs. So uses, the basic idea is from the late 1960s, I guess, by papers from Floyd and Hoare, both of whom got Turing Awards for this and other work. So it involves annotating programs with explicit specifications, especially pre and post conditions for individual functions, although we've extended that some. But we're using the approach that was proposed way back then. It's just that because we've got better technology now, we can automate it. So specifications are written in a mathematically precise language. It's logic. It looks like the move language, but it's a distinct language. Specifications are separate from implementations. So the idea is that the specifications explicitly capture the intent of the user. There are some requirements of the system, and those requirements are implemented by developers, and the way that the developer is implementing those requirements is supposed to be captured in the specification, which is at least somewhat independent of the code in the system. So the process of formal verification is proving automatically that a move program satisfies the specification for all inputs in all states. So formal verification is sort of like testing on steroids or something. So with testing, you always have to worry about what your test coverage, what test inputs are there, what state were you in, what assumptions do you make about the state when you test. And formal verification is all possible inputs and in all possible states. So our goal is to prove correctness, not to hunt for bugs. So this is a subtle point, and it actually took me a little while to realize that I shifted gears. Early in my career, I started trying to prove that things were correct. And what I discovered is that hunting for bugs is sort of more satisfying. So if you want to write a paper saying you found a bug in somebody's seemingly obviously correct design was kind of more impressive than saying, yep, the seemingly correct design was correct. And in particular, the designer of that artifact that you're formally verifying is more impressed because, of course, they thought it was correct when they designed it. And hearing about a bug in the design is much more surprising to them. Now, I said impressed. They're not necessarily pleased, but at least you get their attention if you can find a bug in something that they thought was correct. In our case, we're looking at providing high assurance, right? So we want to develop more confidence in the correctness and lack of security vulnerabilities in our code. So our goal is actually to show that it's correct. We expect that we'll find bugs, and we have found bugs, but that's not the measure of success. The measure of success is, and hard to quantify, but it's how thoroughly we specified the thing, Are we able to verify all our specifications, and can we use that information to persuade people, such as auditors or whatever, that they should have more confidence in their code than they would have had we not done all that work? So let's talk about how specification works. Specification is one of the hardest problems in verification. Verification is a field with many hard problems, many of them computational complexity problems. But one of the ones that's received less work, it's a fuzzy problem. It hasn't been worked on as much as the other problems, and it's one that I'm greatly worried about, is how to ensure the completeness and correctness of the specifications. So errors in the specification are dangerous in several ways. Of course, there are false positives, which are bogus error reports. They don't represent real bugs, but they're annoying and they require debugging either the code or the spec. I'm sorry, if it's a false positive, it requires debugging the spec. The problem is you have a wrong spec. That's okay to some extent. You should expect to have to debug your specs, but you don't want to waste too much time dealing with silly errors that aren't real. More dangerous are false negatives. So because we're interested in proving correctness, we want to go for completeness of our specs and completeness of the algorithms in the verifier. We do not want to miss errors or security vulnerabilities, because that could be much more serious in the context where we're applying this. So one of the ways we're still working on the problem of specification completeness, but one of the ways, the simple things we can do, is enable users to write specifications in their most obviously correct form. So a lot of work in formal verification, including work that I've done, involves clever encoding of specifications to make it possible to solve the problem at all. We'd like to avoid those clever encodings and have people just write logic. So sometimes it's a challenge to get to learn enough logic to do this, but once you know the logic, you should be able to take something you've said in English that's a correctness property and write it down in a logical form that you know is pretty much what you expected. So one of the things here is we use quantifiers for all x, there exists x, freely in our language. A lot of work in formal verification has gone into avoiding quantifiers because you end up with an undecidable problem if you use them, but we just had to bite the bullet and do that for clarity. You will see some examples of those later in the talk. So here's what the stages that processing a verification task look like. So you start with move source code here, and that gets parsed in a typical way to pull out the specifications, which are right now mingled with the source code. We're thinking about separating them, but we haven't made that decision yet. The source code also goes to the move compiler, which produces bytecode. So at this point, we've got an abstract syntax tree for the specification, bytecode for the actual code. And then we process that to pull out all the useful information, put it in various tables and structures, etc. Then we go through another stage of translation that generates boogie code. Boogie I'll talk about shortly. It is a system from Microsoft that defines a language. It's an intermediate language for verification, which makes it easier to go from a real programming language to logic puzzles that can be solved by the logic solver. So Boogie will translate something that looks like an imperative language to logic expressions that can be solved with SMT solvers. So SMT solvers are one of the advances, perhaps the major advance over the last 20 years that makes this whole thing possible. So the ability to solve large logic problems automatically. So if there's a bug in your program, the SMT solver will produce a counterexample to the property you're trying to prove. So that will be an example of some state where the property and inputs where the property does not hold, but it's going to be in the funny SMT language. And so when you have a tool change like this, you need a forward path to do the processing and get the answer to your question. And then you need a backward pass to take whatever diagnostics you get from tools further down the chain and translate them into things that are understandable by tools further up the chain. So we've got the move language, the Boogie translator, and the SMT solver. We get an example, counterexample in SMT notation. We need to back translate that into notation that corresponds to the boogie intermediate representation. That this back translation is largely done by boogie. And then we need to back translate that further to something that someone who is looking at the move code can understand. And so that involves some code to parse the results of boogie and translate them back into an understandable example. And it also involves putting a lot of bookkeeping stuff in the boogie translation so we can actually do that mapping back to line numbers and things like that in the original code. I'll mention that in a lot of the work of formal verification, this ability to debug has kind of been neglected, but it's of course critical if you're, most of the time when you run a verifier on new code, you find a problem, just like running a compiler. And if you couldn't get good error messages out of a compiler, it would really reduce your productivity. So we're trying to solve the same problem for a formal verifier. So I'll talk a little bit about Boogie. It was developed at Microsoft as an intermediate language for verification. So it's between the program level and the SMT solver. So characteristics of this is it looks approximately like a simple imperative language. It has procedures with procedure-like semantics. It has assignment, which update the state. And it has data structures that are based in the theories that are provided in SMT solvers. So that includes integers, arrays, real numbers, recursive data structures, that sort of thing. Okay, and so we have a problem of how to translate bytecodes from the move bytecode language to the Boogie inputs so we can feed it into the Boogie translator. And the way we do that is we implement each bytecode instruction as a Boogie procedure. And then when we translate a bytecode program, it looks like it's Boogie code. There's just a sequence of procedure calls to implement each of the individual instructions in the bytecode program. So a complete translation involves taking the specifications and converting them into assumptions and assertions in Boogie. So an assumption is logically an assumption is something you can use to complete a proof, and the logic analyzer doesn't check that the assumption is true. So when you put it in there, it better be something that's true or that you've proved elsewhere. And the assertions are things that need to be proved. So those are the actual results of verification. I'm going to pause for a moment because there's a garbage truck making noise. Okay.
There is one question in the
yes, please.
Q&A. And the question is move Turing complete?
Yes. So it doesn't, Turing completeness is always tricky. So there's some subtleties to that that we're not relying on. Okay, so first of all, any real programming language is actually finite state when implemented, but that's useless because there are just some astronomically many states that it's easier to consider things to be infinite. More particularly in blockchains, there's a gas limit, right? So when you submit a transaction, you have to give a bound on the amount of resources. So that puts a bound on any loops or infinite recursion. So it has to stop. And what that means is that rather than going into an infinite loop, something that looks like an infinite loop will burn up all the gas that's available and then abort. But we're not taking advantage of that property either. So we're kind of dealing with the Turing completeness. In practice, we don't have that many loops in these contracts. We have some for loops, almost all of which are doing linear search, I think, in various forms. And so we painfully write the loop invariants necessary to verify those things. And we haven't done any proofs of termination, which would in this case be proofs that you don't run out of gas and abort. So those are all problems we should solve, but that's where we are now. Anyway, the language, while limited in expressiveness, is still Turing complete. Are there more questions?
That's all so far.
Okay, good. I hope that means that people are understanding. So let's talk about using the prover. So this will make some things concrete that I've been waving my hands about. So let's look at a particular example of a fragment of a state. So in this state, I've got things happening at address 2, and it has a Diem account object published there, as in the previous example, but I'm also showing a different structure that it has published called a role ID. So this is a struct that's used in access control in our system, which is something we've verified pretty thoroughly. So role ID, there's basically just an enumerated type, this small set of integers representing different roles, including something that corresponds to kind of the root account in an operating system called Diem root. Treasury compliance is one of them, which uh, is kind of responsible for making sure we follow the rules in our treasury. And there are some other roles there as well. Excuse me while I play with my AirPod here. Okay, so if we wanted, one of the things we can do in our specification language is ask whether something is published at a particular address. So remember that I said that you can have 0 or 1 instances of a struct published at a given address. And so we'd like to know if that number is 0 or 1. So the construct in our language to do that is called exists, and then it takes a parameter for the type of thing that might be published and the address, and this returns a Boolean value. Exists here is not a quantifier. This is just whether something is published or not. It's maybe suboptimal naming, but that's what we have. Sometimes you would like to know what values are actually there. And for that, we have another construct called global, which also takes a type parameter and an address. So what it does is find the struct that's published at that address. Once you find the thing at that address, you can start accessing fields and indexing into vectors and that sort of thing using the usual notation. So in this case, we are getting the role ID struct that is published at address 2 and accessing the role ID field, which is just an integer. And then we could make assertions about that, like is it greater than 15 or something like that. For specifications, there's a classical thing from core logic called a post condition. And so we have specifications for individual procedures, and this is one of them. So this is something that is supposed to be true after the procedure. In these things, it's convenient to be able to find out about values of parameters or things that were true just before the procedure was called to, and so there are ways of doing that. So all of our specifications are enclosed in special blocks, so they're mixed in with the source code, but they're put in these blocks so we can distinguish them from the source code. So here I have a function called publish parent VASP credential. VASP is a special type of account that can hold money. It has several parameters, one of which is an address, ADDR. So it's a function that causes one of these credentials to be published at a particular address. So I won't show the code, but I'll show the specification. This is not exactly what's in our system. That's more elaborate, but this is a simplified version. So one of the post conditions is after you publish a VASP credential, there is now a VASP, is called parent VASP is the type for the VASP credential. That exists, it is now published at the specified address. So if this function is successful, that post condition will apply right after the function returns or at the point of return. And then when something is initially published, then the number of children will be 0. So a parent VASP can have some child VASPs underneath it, but when the parent VASP is born, it doesn't have children yet. Another type of post condition is called aborts if, and aborting is kind of a different thing in blockchain programs, smart contracts. So instead of runtime errors or exceptions, move programs abort. And so a runtime error would typically be an integer overflow, but the move program quits and backs out of everything it's done. So it goes back to the previous state. I just said that. So programs are supposed to abort under some conditions. So we like to be able to specify this. So a verifier should not report an expected abort as an error. So if you expect an abort to happen when you code the thing up, you don't want the verifier telling you that's a problem, because it's not. But an unexpected abort is an error. Also, if you expect an abort to happen and it does not occur, that is also an error that you want to know about. So the abort if specification captures the programmer's expectations about aborting. Here's an example. So this is access control. So a parent VASP can only be created by an account with a Treasury compliance role. So we can specify that in aborts if. This is enforced by aborting if the creating account does not have this Treasury compliance role. So we say it aborts if we get the role ID of the creator address, which is another argument to create parent VASP account. And if that is not equal to a defined constant, which is Treasury compliance role ID, now I have to back up. Okay, Treasury compliance role ID, then we abort and we provide a diagnostic to the unfortunate person who sent that transaction, which says that it requires a role, particular role to execute, and that requirement was not met. So we can specify these abort conditions, and unless you turn the feature off, the prover will check that your abort conditions are complete. You've covered every possibility. So those are what I call local specifications. They're associated with individual procedures. The global specifications are frequently more important. And so those involve multiple functions and they involve properties of the global state. So they talk about change or lack of change over time. So in a sense, they're temporal properties. So we have two kinds of global properties. We have global invariants, which are properties that are guaranteed to be true for all time. And we have two-state invariants, which are properties that compare the previous and the current state after a single instruction. So here's an example of a global invariant. We want to say that every address that has a Diem account also has a role ID. The role IDs are used for access control, so you should never have a Diem account that doesn't have a role ID. And so we can write that in our language by saying spec module. So that means this applies for the entire module, all of the procedures in the code in the module. And we say it's a global invariant. We say here's a universal quantifier. So for every address, if there is a Diem account published at that address, then there's a role ID published at that address also. So there are effectively infinitely many addresses. So this is something the prover can prove because it sees how you've changed the addresses. If this invariant is true before an instruction is executed, then you're just publishing a Diem account at one place, and so it can check there that you have the role ID already when you publish that new Diem account. If it was true for all addresses except the one you just changed, then it will continue to be for all addresses after that. Here's an example of a two-state invariant. So they can refer to pre and post states of a state change, so the state before and after an instruction. And so you can, I'll give you an example that I think is surprisingly expressive for something so simple. So we say once a role ID is stored in an address, it never changes. So you define the role, it stays the same forever. So we write that as a two-state invariant where we say for every address, if in the previous state there existed a role ID at that address, then in the next state, in the current state, there will continue to exist a role ID there. Furthermore, the value of the role ID field of that role ID is going to be equal to the value in the previous state. So it says it can't possibly change. Once the thing is defined, it continues forever because this is going to hold for every state in the blockchain. So I'd like to talk, I'm running, I want to wrap up pretty quickly. So I'll talk quickly about one novelty of what we're doing, which is how we handle memory. So one of the big problems in static analysis and formal verification is dealing with aliasing in memory. And the problem there is basically if you have a bunch of pointers flying around that could point to the same memory location, you have to do your proof under considering all the possibilities of maybe two pointers point to the same thing or maybe not. If you have 100 pointers, that's a lot of pairs of pointers that you have to reason about. And so this can result in a combinatorial explosion of possible aliasing relationships. And the typical approach, which I've used in previous systems, is to model memory as just a big array and model pointers as indices into that array. And so you get deeply nested array store expressions. Every time you update an array, you're building up a bigger and bigger expression, and you can get massive trees of if then else's covering all possibilities of whether pairs of things are equal or not. And that causes computational burdens. So in Move, we can avoid aliasing because of the restrictions in the language. Memory is tree structured. We have records of records of records. We can't store memory references in memory. We can't have pointers to subtrees stored in memory. So those can only be stored on the stack. And so the actual state is a tree, not a directed graph. And we also have this very strict static analysis thing called the borrow checker, like an extended type checker, that strictly forbids combinations of references that result in aliasing. In particular, if you have a mutable reference, which allows you to change something, there can't be any other references to the same thing, mutable or immutable. So this essentially means even though we have these references, we can use copy semantics. So this is what it looks like conceptually in the prover. Suppose you have a data structure. It has a subtree that's another data structure, and you have a mutable reference to that other data structure. Suppose you have a function that takes that mutable reference. Then you can kind of ignore the rest of the tree, copy, imagine you have a copy in parameter for the subtree T2. Your function f can make whatever changes it's going to make to produce a modified tree, and then we can pretend that just gets copied back to the original T1. So that simplifies our verification task. So first of all, the reason we can get away with this is that there's no way you can write move code that can distinguish this way of doing things from just making the modification in place in T1, okay? And the advantage to us is that it greatly simplifies the verification task. So it eliminates this combinatorial explosion of aliasing possibilities, and it greatly simplifies framing. So framing is you, in addition to specifying what changes when you call a function, you have to specify what doesn't change. And you don't want to write that out explicitly. You want to be able to infer it. And so because we know we're just copied in a small part of a tree or something, then we know nothing else changed. And it makes it easier to infer what does not change when a function is called. And so it basically gives us the convenience of imperative programming with some of the advantages of functional programming. So I'll wrap up now. I should mention that there are similar projects, and they're good projects, and there are many efforts to verify stuff on blockchains. I'll talk about things that are most similar to what we're doing. So verifying smart contracts on a blockchain, doing automatic verification based on these logic solvers called SMT solvers. And so one of them is Verisol, which has been developed at Microsoft Research. Another one is SolC Verify at SRI International. And the third one is Satora, which is a startup with proprietary technology. So, but I believe it's pretty much the same general approach. So the differences between these and our system is that they're based on the Solidity programming language that runs in the Ethereum blockchain. So the issues in Solidity are very different from the issues in Move. And honestly, we took Solidity as an example of things not to do because it's very hard to verify, and there have been a lot of damaging bugs in Solidity code on Ethereum. So basically, we've got an easier job, and maybe we're able to do more because of that. The current status of the project is that we've written extensive specifications for the code we expect to deploy as part of the Diem blockchain. So that includes the Move standard library and something called the Diem framework, which is all the contracts that basically do everything. So we specified and verified all of the access control requirements, which were separately documented in something called DIP2. And so this was a document to explain to lawyers and other engineers how our access control was going to work. And we could start with those as requirements to just code them up in our language and prove that all of them were true. We found some bugs doing that process. We also specified and verified the APIs of our transaction scripts, so particularly the abort conditions. So we found some places where the documentation forgot to mention some possible aborts or mentioned aborts that couldn't actually occur. And many, many other properties, various things that programmers thought should be true. All of our specifications verify completely automatically at this time, and it's 30 seconds or less per module. Formal verification is automatically run during continuous integration whenever we check in code. And if you're curious, it's all out there in this repository on GitHub in the language subdirectory. That includes all of the code for the transaction scripts, our specifications, and the prover tool. We've got the prover out there. We're not supporting it for general use because we're busy making sure we can use it first, but maybe next year we'll be able to do that. The system is rapidly evolving, so that's another reason we don't want to encourage people outside Diem to use it. Okay, so the next challenge, I think, with the prover is to try to maximize the benefit while minimizing the cost. So we've proved that we can do it. We've not proved that it's kind of that it's cost effective to use it. So we need to make it more usable, basically, and make users more productive. So we've got a lot of specifications there that aren't going to detect errors. They just make the prover run faster. So we'd like to infer those automatically. And we'd like to have better debugging when people run into problems, although that situation has gotten a lot better over the last few months. There's a research problem of inventing tools to check for the correctness and completeness of specifications. I think that's something that lots of people could look at in lots of different contexts. It's been a neglected research topic in this field. And there are many other engineering improvements that we would like to make. So at that point, I can wrap up. So move programs, smart contracts, hit the sweet spot for formal verification for the reasons I cited earlier. Impacts of bugs can be very bad, so it's worth doing. Move programs are relatively simple, so it's not as hard as it would be with C++. Starting with a clean slate makes the problem easier than it would be. Our approach is a highly automated Floyd-Hoare verification method. And move in the Diem blockchain creates some unique issues and opportunities. So with that, I'll wrap up and say thank you. I'm sorry I went about 5 minutes longer than I expected to, but I hope we have some time for questions.
Thank you, David. That was a very clear presentation, I think. I don't see, oh, there's a question. Are you still using Rust?
Yes. So the system is written in Rust. Now we're using Boogie for which we're using some external software. So Boogie is written in .NET, C# or something, and the SMT solvers are written in C# or C++. But our code is written in Rust.
I don't see another question immediately there, but I'll ask one. I think one of the interesting promises of formal methods are generally for better security, not simply blockchain. And blockchain really, I think, has more limited uses than are being advertised. But how well does some of your lessons from this generalize to other software, including process control, real-time secure concerns, and otherwise?
You know, having done this, except for my advancing age, it would be great to go back to some of those problems and apply what we've learned. I'll tell you what I think is the major barrier. I mean, there's been a lot of work on formal verification of these kinds of systems. And I really think, you know, I knew it was going to be a benefit to be starting with a clean slate, but I realized how important it really was once we got into the project. You know, there is so much legacy code and working with people's programming languages, development practices, and the existing systems that were not designed for verification is a huge problem. So verification is the hardest problem in this space, a formal verification. And so I think you need to optimize everything else. If you want to have formally verified systems, you need to optimize everything else to make the systems formally verifiable. And so it's difficult to adapt other people's tools that were not designed with that in mind to work. So I think you can try to evolve them, and people have done that. Particularly, you know, I'm very familiar with the hardware world, or at least the hardware world of over a decade ago. And there, the idea was to take languages that were written for synthesis of hardware and simulation of hardware and define subsets of them that could be used for verification. So you can adapt existing languages, but there is a chicken and egg problem, right? If people don't realize the value of verification or they haven't seen a demonstration that it can actually work, then it's hard to get them to motivate making the extensive changes that are necessary to really support it. So I would say that the route to formally verified control systems, for example, would involve a long iteration of people trying to build verification systems and then people modifying the languages or making new languages to be more verifiable. So I think you have to do what we're doing, which is co-designing the languages, the programming methodology, requirements methodology, which I haven't really talked about here, but we've kind of neglected and we're going to be paying more attention to in the future, and the formal verification tools. So this is really a grand challenge problem, and we should not underestimate the difficulty of it. But I think it's needed to be able to formally verify stuff, and I believe it's feasible, at least technically, if we can get all the planets aligned.
Great, thank you. We do have a question here. What guarantees the uniqueness of addresses?
In what sense? So the addresses are numbers and different numbers are different, but that's a flippant answer. So, so maybe the most important thing published in an address is an account. So that's a struct. So you can't publish more than one account as an address. If you try to publish something in an address and there's already something published there of exactly the same type, the transaction aborts. And so what that guarantees that the first creator of an account owns the account and nobody else can set another account there. Does that answer the question?
I'll need the questioner to respond to that, maybe in the chat. Did that respond? Yes, thank you.
Okay.
And that exhausts both the questions and the time we've set aside. Thank you so much for visiting us today and providing the talk. It's refreshing to hear. And hopefully we'll get you to visit us in person at some time in the future.
Yeah, I was going to mention that. So thank you for inviting me here. You know, it's efficient to do these talks from my home office and whatever, but I've, been invited to give talks to various universities when I was a professor and whatever. And I always loved having those visits where you could talk to other researchers, just talk about my work, of course, but find out what other people are doing, find out how they run their departments and, what's happening there and that sort of thing. So exchange professional notes on everything. So those kinds of visits are really wonderful. And I'm hoping we can get done with COVID so we can restart that kind of activity.
Very much agreed with that. So thank you again, and we look forward to talking to you at a future time. For everybody who's on the call, we have another one of these next Wednesday. Nasir Memem from NYU will be our speaker. And until then, have a good week and stay safe.